Hello folks, this is Jeffrey Fox here. We're going to talk about optimization. This is actually a pretty old area. I started working on that as an undergraduate and graduate student over 50 years ago and published my first paper in this broad area. And we will talk about some broad concepts such as objective functions, models. We'll spend quite a lot of time on models because one of the remarkable things about deep learning is the type of model it has. It's sort of different from the models we had in the past, and actually sort of easier. And then we'll talk about obnoxious things such as local minima, avoiding it with annealing and tempering. And we will note that everything in the world is an optimization problem. Actually, as you're listening to this, you're solving an optimization problem of how to get the best possible grade in the least possible time in this course. I will give examples of objective functions and greedy algorithms. We'll talk about distances, which underlie a lot of optimization problems. You're trying to make distances between things small. We'll look at different types of parameters, discrete and continuous, genetic algorithms aimed at mainly discrete problems, and heuristics, which sort of everything is. All right, let's get going. This is Jeffrey Fox. Here is my cryptic picture just here. And we're off. Okay, so these are again the terms we'll learn about here. We've already effectively said these. And notice that, we'll note later on, there's actually, although technically we're doing optimization, we're actually doing minimization. We can always turn, actually, most people maximizing things. You're maximizing happiness. You're maximizing your salary and things like that. So usually people are maximizing things, but we can always take the negative of happiness, namely unhappiness, and minimize unhappiness as opposed to maximizing happiness, and so on. Okay, so I think I've mentioned every single one of these things already on the first slide. All right, so let's look at some features that an optimization problem has. So it always has a function or maybe collection of functions that can depend on, when I was doing it 50 to 60 years ago, they were tens and possibly hundreds of parameters. Now they can go up to billions of parameters for a deep learning network. I've already noted that optimization can always be thought of as minimization. An important feature of the thing we're trying to minimize is that it's often positive. Now, that's not true about, say, happiness. Happiness can be negative. In fact, maybe it usually is. But when we're dealing with mathematical functions, we're trying to minimize. Often they're positive because they're constructed as a sum of positive things, such as the sum of squares in classic least squares optimization. We have continuous parameters, which are probably the most important. When we do deep learning weights, they're continuous. When we're doing cluster centers for clustering, they're continuous. Expectation maximization tends to deal with continuous parameters. An example of discrete parameters in the deep learning case is called hyperparameter choice. The number of layers in your network is a discrete parameter, and you can choose, and you have to optimize that. Often using genetic algorithms. The nature of genetic algorithms make discrete choices. They change the genes and things like that, representing the solution. Those changes are discrete, not continuous, and as such, genetic algorithms are good for the discrete problems. As we mentioned, there are a variety of different methods. When I started, I actually used methods to involve second derivatives because I thought I had to be strong. Calculate that second derivative because I could do it. Other people use functions, which I didn't respect. Actually, today, neither of us are right. The dominant method is you calculate first derivatives, and it uses something we never actually respected in the past, the so-called method of steepest descent. But there's been a very clever adaptation of that to become stochastic gradient descent, which is much more robust than classic steepest descent. There's some problems which are actually pretty easy, such as finding the minimum in a line, and that sometimes involves is used as a sub-problem. You find a line you want to minimize along, and then you just minimize along that line. That is typically used by done. Actually, that can be done just with function evaluations very easily. You start at one point in the line, find a second point, then you use a bisection method. You find a point in the middle. Then you decide which part of the range to look at. All right. Now we have the different types of methods. I say the fastest method involves second derivatives, and that ought to be true. It involves more work on your part. You have to calculate first and second derivatives. As I was shocked to find when I started working on this field 50 to 60 years ago, it always diverges. Even the simplest problem diverges, at least it did for me. And there is a very subtle point that for the least squares problem, a second derivatives of the total entity only needs first derivatives of the things that form the least squares. An important area is constraints. Often you're solving problems that have constraints. You want to I don't know, maximize the position of power and ruthlessness you have, but minimize the negative opinions of other people. So when you have constraints, they're actually often hard to put in, and typically you have a penalty function. You take your thing you're really trying to minimize, and you add a term called, which is a constant times something which grows as the constraint gets violated more. So if you wanted to minimize function f subject to the condition that g is negative, you would add in a constraint that you would add a constant times the square of that function g if that function g is negative, so that a large negative value of g causes the objective function to increase. This is a well-known heuristic. And it's not exact, it just is an effective way of solving the problem. So that's a general thing we have to do. Okay, now we have slides on individual components. Now first on actually a general idea of minimizing a cost function or a loss function, or it's just a lot of this is based on analogy with physics on minimizing an energy. If you Mother Nature, physics was always either minimizing energy or free energies, and so a lot of, if you take something like a least squares, especially minimum sum of least squares, that's very like a physics problem. So we're trying to find the parameters. We have the energy, which is a function of the model. The model has parameters, making it more, telling you exactly how the model is set up, and you need to minimize the energy function given in terms of those parameters given a set of data. Then we have, as we'll see, global minima is if the energy function is a sweet little convex function, then the minima is very easy to find. Just go down the hill and find it. If the global minimas are along a narrow winding valley, that's pretty difficult. And if you have to jump up on top of another hill to find an even smaller minimum in a valley across the road, then it's terrible. And we do not know how many false minima there are, what their nature is, and we will give you some pictures to try to quantify that later on. And sometimes one even does actually some sort of search over possible initial starting points to find global minima. That's that is done implicitly or explicitly in many cases. We've already mentioned the energy function is bounded below, and there are particular heuristics or ways of doing things which find appropriate for particular types of projects, problems, and notice we're only looking for good solutions. We do not need the very best solution because the data is intrinsically inaccurate. And so there is the exact solution for the set of data is not important. What you want is a solution that's as good as the data. And it's actually quite hard. So that's good. It's actually, of course, pretty hard to know whether your solution is good or not. You can sometimes find errors, but that error is only a local error. It tells you how much the energy function changes as you change the parameters, and that tells you and gives you an error. But that doesn't tell you there isn't a better solution further away, which is sort of a bias. All right, so that's energy minimization. Okay, so in the general formulation, we have our loss function, or energy E. It's a function of parameters. These parameters are essentially the parameters of the model. So we can think of the model as having parameters. And as you mentioned, sometimes this energy is the least squares sum, which is illustrated here. The sum of the difference between a data value and a model for the data. The data points are labeled by I, the model is labeled by X as parameters, and then it's we need the expectation of the model for the data point I. So the simplest model is just say a linear regression is effectively linear on some I, where I say if I is a year or something like that, some parameter of the model of the data. And these things here, A and B, are the model. There's a simple model. The thing is linear as a function of year or something. Then we have a set of data values labeled by the I. That's the so-called training set. And if we look at deep learning, then of course deep learning is not a simple linear regression. It's something we'll see a picture of soon. It's a neural net. And this particular E is clearly positive definite because it's sums of squares. And then the set of data values is the training set again. So, okay, let's continue this discussion of how we minimize a function E, which is has these parameters it depends on x1 to xk, which define the model. And we want to choose those parameters to get the smallest possible value for E. And to do that, there's a space formed by these x's. May or may not be vector. That typically is often a vector space. And we just have to run around that space finding the smallest value. So we have to explore the space, navigate it. And we're going to look at now the methods that use derivatives. And the best known method and the one that's effectively used by deep learning is called steepest descent. And steepest descent is very straightforward. You're at a position x, you calculate the derivative x, you move in a direction which is in the direction of the gradient. If you think about that and think about sitting on a hill, moving in the direction of the gradient is going down the direction which gives you the best value for the buck. Namely, it gives you the biggest decrease in energy for a certain size shift. And that's pretty interesting because you want to keep the shift small so that you don't diverge. So that's why it's called steepest descent. The only trouble with steepest descent is, let's think of the Grand Canyon. Grand Canyon has a pretty clear steep descent. It goes down to the bottom of the canyon. Unfortunately, if you want to find a minimum, which is along the side, the bottom of the canyon, back in a different state or something, then you'll never find it with steepest descent. So this is an important plus and minus of steepest descent. So another important feature of steepest descent, that the energy is actually guaranteed to decrease. That's good. If it's steepest descent, where you certainly want it to decrease, it will not be very steepest if it increased. And mathematically that counts because you start off with a certain value of x, you shift the x by these delta x's here. This is the delta x's. Well, this part here is the delta x. This is x plus delta x. And then we find that the new value of the energy is proportional to the sum of the derivative squared. So this is positive, and so this constant is positive. If we go down the derivative, and then the minus, we've already put the minus sign in here and here to make certain we go down. So I should have said this is a positive constant. Of course, the shift is small if we're near the minimum. That's good. We're near the minimum. And on the other hand, if we make the constant too big, then it is possible that we have a problem, because if we think of this as a Taylor expansion, there's another, the next term is 1/2 the shift in xj times the shift in xk summed over j and k times this second derivative. And that could be big. And in fact, my experience is it's typically unreasonably big. And so one has to keep these shifts pretty small. There is a set of very well-known, wonderful methods which actually are very old. I remember employing it's an REU project in an undergraduate at Caltech to do a survey of these methods for trying to do optimization. This fellow was a brilliant student, a Caltech physics student, and he actually went on to Princeton to do extremely well on a PhD. But anyway, he found to me the best methods, which was McQuart's method, and which I then actually used to analyze a very large physics experiment. By those days, large physics experiment. By these days, it will be a small physics experiment. And that actually used one of these methods I'm not so positive about on this page, which will use calculating second derivatives. The problem I had was this physics experiment, which was measuring the consequences of when photons hit lead. And then we wanted to when we had a lead array, which actually measured X and Y, but it had several photons hitting the lead array, and you had to match the X's with the Y's using the amount of energy deposited and things like that. And in this case here, the photons came from the decay of pi0 mesons or eta mesons or eta prime mesons, and we were able to measure them very accurately. And I ran hundreds of thousands of events through this fitting program, and on each program I found many photons. Anyway, so that all worked using second derivatives. But in those cases, I probably had here, I think I went up to 5 particles, or maybe 5 particles. So that would be about 10 photons. Each of them has an energy and a direction, which was 2-dimensional. So they each had 3 parameters. So that was something like 15 parameters. As I said, in those days, we were doing sort of very precise problems with a relatively small number of parameters. But we were running them on sort of big data. We had hundreds of thousands of events. Nowadays, of course, the people have billions of events. But anyway, those days it was quite big, and we had hundreds of magnetic tapes holding the data, which tapes were all thrown away one day. And all those results are unreproducible. Anyway, never mind. If we look at the problem with the method which uses second derivatives is that you can use Newton's method, which gives you an absolute shifting x, because you get a quadratic approximation to the function involving d dx and d squared d dxj dxk. You can then solve this as a matrix equation for finding the shifts, and you will solve it, and you will get absolute shift predictions. Then there's some problems. Well, a very obvious problem is that this, if you have 15 to hundreds of parameters, then 100 by 100 matrix is not so big. But a billion by a billion matrix is pretty big. So if you have lots of parameters, it doesn't work. And We are calculating absolute shifts with Newton's method, but we're ignoring the higher order terms. And these higher order terms can be there. And in fact, they are there, always there. And they always cause divergence in the naive method. So there's a method called Macquart's method, which is out of scope for this class, but I spent lots of time on and improving and things like that. It actually tries to ensure that you avoid these divergences. In the terms of my Grand Canyon analogy, it was by ensuring you went down, roughly down to the bottom of the canyon, and you minimize the amount of effort you spent going along the canyon bottom. Because the trouble about going along the canyon bottom, it's a very flattish thing, might have a gentle slope, and they might have a true minimum, but it's off there. Whereas down is much shorter distance. And the trouble is, the mathematics doesn't understand between big undetermined directions and small well-determined directions. And if you include the big undetermined direction, it will completely overwhelm the small direction, and you won't even get to the bottom of the Grand Canyon. But with Macquart's method, you will. It makes certain that you ignore these undetermined directions. All right. So in the case of deep learning, it's actually impractical to find the second derivative, so all this is irrelevant. As another aside here, the Taylor expansion is a polynomial approximation. And I told you its problem was it diverged because we had x cubed terms, or x to the fourth and the fifth and the sixth and so on. And in those days, we were learned to abhor polynomials. Deep learning definitely abhors and then does not have a polynomial representation at all. It has these activation layers which put cutoffs in there, so it's a very much more robust approximation method. So all these very simple ideas about how you approximate functions are very important in practice, because there are methods which have very different reliabilities. All right, so now we come to some nice pictures of typical functions. Well, here is a nice function. It's convex. Wherever you are here, it's pretty obvious you're going to get to the minimum, okay, because you just slide down to the bottom. And you have no problem with long valleys. Here we have, over here, we have a more serious problem. We say we're up here. How do we get to this minimum and avoid, say, this minimum, or avoid even not so, the one that's almost as good, that minimum? It's very hard, because you only can see these deep minima when you get sort of near them. And when you're up here, well, just think about looking at out from your mountaintop. You may not see inside the valley to see that really this valley on the left side really has the lowest minimum. It's not obvious at all. And what you see and when you're looking at the top of a hill is even more true with lots more dimensions and a multi-dimension, billion dimension function which poor old deep learning is looking at. So this is this thing here is how you think, but actually what you should be thinking of is something more like this. Oh, here we go over here, so you can see these are actually older. This was a talk I gave in 1992 in Houston, but it's actually was earlier than that. I was at Syracuse University at that time. Anyway, I was pointing out the difference between there were various types of local minima. The local minima we like are these ones. You have a big minimum, and the local minimum is a little glitch on the way down to the bottom. Like if you're falling down the Grand Canyon and you have a little ledge, that's a local minimum. Those are actually not so difficult to jump over, and that's sort of what steepest descent, what stochastic gradient descent jumps over. This one here is more serious, because this is a perfectly valid minimum, and there's nothing in foreseeable distance which is anywhere near as good as this one. But actually, globally, we know this is the right answer. And it's actually better than this, which also looks pretty good. So when you get deep minima, and you also see that here, this minima here compared to some of these minima over here may or may not be the best. And so these types of, I call them grand challenges in optimization in 1992, because grand challenge was a word we like to use then. These require different techniques, which would be searching over different starting points or searching over different choices to try to actually find, because you're almost certainly going to go to whichever of these sharp minima is nearest to where you start, or not necessarily nearest, because you might actually diverge. So you might actually jump a big distance, say from here. If you were here, you might in the first step jump to here. Who knows? You can do all sorts of things with with these irregularly shaped regions. So that points out the types of challenges. I say these are the ones you actually work on, these challenges. Ripples on an overall global minimum. Okay, here's a recent blog I read on medium.com, which discussed in detail actually visualizing the loss function. And they had a lot of quite pretty here animated GIFs, which I showed two examples. Notice this one's a pretty nice funnel shaped, whereas this has a more elliptical structure, elongated. And actually the different ratios of the slopes in different directions is one of the reasons it's very hard to do good optimization, because it's difficult to train systems that actually automatically choose the right slope in each direction. So these are just two examples. I should recommend you read the this article here, and that has much more detail and also many more animated GIFs. Okay, thank you. So this slide here says what I've roughly said already. Here we have our energy function, which I pointed out that everything in life is an optimization problem, and most of your life you're probably trying to, I don't know, either trying to make yourself important, rich, or happy. Hopefully you're trying to make yourself happy, in which case what you're trying to minimize is the unhappiness function. So that's what I put here, the unhappiness function. And here you are, you actually must be pretty unhappy because this is rather a large value. And now we're trying to make yourself happy. Well, you might make a mistake and end up here, whereas you really want to be here. I mean, here you have the parameters you'll be determined, which university you go to, who you marry, things like that, which school, the school district, what's the quality of the school district. These are all functions, parameters to be determined in one's to make one's life unhappiness as small as possible. Here's an interesting slight aside as far as this course is concerned, but it's quite important in practice. Namely, Mother Nature actually, and the whole Industrial Revolution sees this every day, because when you make steel and steel manufacture things, you heat them up to be able to work on them better and get them in the right shape, and then you cool them down. Now, when you cool down, you can do it very fast. That's called quenching. And when you do that, you sort of keep it in the state it used to be. It doesn't have time when you cool it fast by just flinging it in freezing water or something. You will often find that the atoms get trapped in the wrong place. So here you see here are some beads. These things are colored because this thing was not annealed. It was cooled very quickly. This one was cooled very slowly. It's much more uniform. And typically, non-uniformity leads to, in the case of manufactured items, it leads to steel or whatever you're making, which is not as strong, because the fact that the atoms are in the wrong place means they're not they're not at the correct minimum. They're actually above the minimum, and so they're going to really want to get to the minimum, and that means it's going to break easily. So if you want to have very strong steel, you better use annealing or tempering, which is a variant of annealing. And that gets its results in a clever way, which is sort of mimicked a little in the stochastic gradient descent. Namely, at a given temperature, you just keep it at that temperature for a while so that the atoms can wander around using the the Brownian motion at that temperature to find the right minimum. Because they're always going to look for minima. And if you do too fast, they don't have time to find the minimum. So it's also amusing to notice that when people are keen on quantum computing, actually there's a subset of quantum computing which is a little more practical, quantum annealing. Because if you build a quantum computer which has quantum states in it, those quantum states do physics things, so they can actually anneal and find out minima using annealing techniques by just cooling themselves. Okay, in this slide here we go into a little bit more detail on annealing. Here we have our loss function, our unhappiness. Here we have some single line which represents the billion parameters or 10 parameters that define that the loss function depends on. And here we have a sort of plot of the loss function at different temperatures in this configuration space. So for very high temperature, T1 is the highest here, we get a very smooth function. Temperature smooths things out because the particles are just moving around. And KT is the measure of the mean value of velocity squared of this random motion. And so the more T is, the more they move around, going like the square root of T in velocity. So this smooths out these little glitches. And so if you're up here at high temperature, then you can easily get your way down to here. At lower temperatures, you get these glitches fed in, where this sort of when this thing is energy in the case where T is really most applicable, then this size here depends on the value, how KT depends on the energy difference represented here. So this being a sharp glitch corresponds to a relatively small t, because KT has to be a measure of this distance here. And as we go lower and lower in temperatures, we get more and more of these little glitches. And it's harder and harder to find what we do here. But then what annealing does, it sends us down to the bottom. We start off at the high temperature at the bottom here, and we just move along here. Whereas if we immediately go to a very low temperature, we end up here. We can't, whereas from here we can go to here. From here, we go to that. So this points out that annealing gives us a path to get correct minima, and whereas a fixed temperature or quenched approach gives you false or local minima. There's a whole set of approaches to optimization built around these ideas, which I wrote several papers on. All right, now let's get back to models. So most of my early work was actually building models. I was called a phenomenologist, and by a biophenomenologist, it meant I built models which I compared with experiment. That's what phenomenology was. Taking the best you knew about theoretical physics, use it to build a model, compare it with experiment to make deductions about the model. There we cared about the model. In case of deep learning, we don't care about the model because the model is just a parameterization. So these old models came from physics or some understanding of what's going on, and the parameters of the model are things like mass of the particle, velocity of the particle. Now there's some physics in today's models, at least in the results of the models, because you're predicting how to turn the wheel, which is controlled by physics. But a lot of what's done today in big data is not to do with traditional physics like how a car drives. It's to do with a complex system, the set of all viewers of YouTube, or the set of all shoppers on Amazon. And you need to look at things like recommender systems, which tell you which movie to watch, which product to buy, and things like that. And the original approach to this was something like the K nearest neighbor method. You find the K options which are near to what you're viewed as being looking like, and that was basically a sort of physics-like approach. You try to minimize the distance in the space, and that was the original model. But no, these have been replaced by deep learning, which basically parameterizes the whole watching of movies, and it puts in what you watch and what other people watch, and that's the new model. And the new model is a pretty complex deep learning network, which you can read about actually in the course notes on that. Although they're not trivial. They're not. I'd rather work on theoretical physics, but anyway. We can't work on theoretical physics if we want to actually sell adverts on YouTube. All right, so this just here is a sort of rather quaint return to the past for me. So here I have a paper with Feynman, Field, and myself. It has lots of citations. It was a reasonably good paper. And now look at what it says here, comparison of a QCD model. So this is equivalent to the validation data set or the testing data set. And these things here are experimental observations. There are lots of them here. And it doesn't really matter for you what they measure. They're measuring some cross-section on a log plot. And it's just a function of a certain measured parameter called the transverse momentum of a certain particle called the pi meson at a certain direction, 90 degrees. And this is comparing the predictions of the model. So the model has been trained on other data which are given us the parameters, and then we use that model, which has a mix of theoretical physics in it and a mix of data, because you cannot, given theoretical physics, which is this fancy thing called quantum chromodynamics for this type of reaction, you can't get a rigorous prediction from that theory as to what is being observed. You have to make models which approximate the theory or have enough parameters to go from what we know theoretically to what we observe. And so you see we actually reproduced our testing data quite well. Not perfectly, but the data itself has quite a lot of errors. This is difficult data to measure. It's a very small cross-section. And this used a large chi-squared fit, and so it actually minimized an energy function, which was the chi-squared least squares quantity, which measured, not in this case here, it did that on other data. This is the testing data, where you found the model, you take the model predictions and compare with the data. And we've shown how we actually choosing different parameters of the model, you get answers which are not as good. So that's and these things here, lambda, are important physics parameters that you need to know. So here we have more examples here. There's a so-called Reggi theory model, which Tullio Reggi, a famous theoretical physicist from Italy, developed, and I extended to this type of problem. And this says here is these are experiments I did with others at Fermilab in Illinois, which has a large accelerator, and these are comparisons of a model with the measurements. And actually, we see that the model does well for small values of this parameter t and does very badly out here, which said the deduction of this experiment was that this famous theory was needed modification to explain this effect here, but it was actually a fundamentally correct theory, because where most of the data which was here, it agreed well. And here's a similar result. So it's actually more like the previous plot, where this was the difference is this was an experiment I did, E260. Doing experiments at Fermilab is hard work. You stay in Naperville and places like that, and stay up all night monitoring the apparatus and things like that. I built all the software to do the simulations to analyze this data. So I was quite pleased or proud of these results. And we were the first people actually to show these huge increases. Here's the top search result. Hey, that was Google Assistant telling me that I somehow had triggered it. Oh well, I don't think it had any very deep comment to make. It needs better AI to tell it when I really want it. So let's continue. Anyway, so this huge increase here from between these triangles and the squares, which are the difference between the jet cross sections and the single particle cross sections, was a major prediction of the model, and it confirmed the validity of quantum chromodynamics, which is now agreed to be a solid theory of particle physics. And this experiment was one of the very first to show that. Now there are much better experiments at the CERN collider, which has far higher statistics and goes to much higher values of this transverse momentum, when the results are much more impressive. We were, however, first. We just got a scruffy answer first. And this is the Field-Feynman-Fox model here. I gave you that paper earlier. Here's another interesting example. So I have this paper with Stephen Wolfram, who is obviously far better known than me. He was a student at Caltech at the time. I was a faculty there. And we worked together extensively and wrote several papers. And here we have, we introduced some parameters called HL, the so-called Fox-Wolfram moments, which had the property that their value could tell you about the underlying physics of the problem. And this was a pretty simple observation, and we did lots of model calculations to show what the value of HL should look like. So now this group, which includes people from Caltech and Fermilab and CERN, working on these giant new accelerators, has produced a new deep learning way of trying to do what this was trying to give a value, find variables whose value told you what was going on in a deep level inside the event. This is just a deep learning model where you train it and it tells you which events are of what type. Notice this very old paper, 1978, has still had 47 citations in last year. So it's still, and the reason is it just it gives a very simple, clean way, and people are still doing these experiments that they still need to identify which type of particles are what. Whether we'll continue any citations is not so obvious, because this JettyNet replaces what we did with, I think, a more powerful method. And what it's trying to do is trying to distinguish various classes of events. This is just one jet. Here we have two jets, and here we have three jets. And we had moments to try to distinguish these, but the JettyNet is a much more precise approach, in my opinion, and more likely to be successful. And I think it's interesting that finally, after what was 78, that is 40 years, we are finally improving on this analysis from those days, which was well, the fact that 1640 citations says it's been used by physicists to analyze data for some time. So here we have the little digression on what a model is. And so here I had a paper for Stephen called A Model. So this is something about models. And it was a model used to help identify these different classes of events we described earlier with these moments, H sub L. And here's a picture of the model. This is the hidden variables of these the things which are dotted are gluons, and the solid things are quarks. And here we have them roaring off and breaking up into pions and things like that. And we take this set of hidden variables, the parameters of these quarks and gluons, and we convert them into particles and then compare them with experiment. This is at a very high energy, well, by those days high energy, and rather low energy here. And there are more quarks and gluons and more observed hadrons at the higher energy. And just as an, one does, one thinks about nanometers these days, and these are all at the level of femtometers or Fermis, which physicists would call them, which are 10 to the minus 15 meters or 1/1,000,000th of a nanometer. So nanoparticles are much bigger than this. These are the fundamental protons and things like that, which are of order Fermi. Nuclear physics. Things like nuclei are set much bigger, like a gold nucleus, I think, is 8 Fermis in size. But a single proton's around a Fermi, and pions are somewhat smaller than that, but they're all around that size. So Fermi is the unit for the action. So you have the hidden variables happening at the level of a Fermi, which you can't observe, and those hidden variables, the parameters of these particles, determines what you see. So that's the original type of model which we did, and it's not. Anyway, you can go online to see what I wrote and get more on that. But I just wanted to point out that the basic understanding of this of optimization has been very well known for a long time. So those notes were from, let's say, they were pretty mature in the early 80s. So at that time, I think I was at the leading edge in the field, and so that would say that this has been well known for 40 years. Now we come back to optimization. So if we look at optimization, we have various methods, various problems. One we do is looking at radar data to try to look at snow. If you look at snow, you see layers because you have a season's worth of snow. It freezes. There's a hard top to the snow. The next snow falls on top of it, and so you get a whole set of layers. 1 layer per year, and you need to analyze how much snow falls in each year. So you have to identify the layers from the radar reflections. Clustering is finding the positions of clusters to minimize the sum of the squares of the particle position minus the center position. Dimension reduction, which is assigning typically Euclidean positions to particles or entities. Sorry, not to particles. You take any odd entity defined in an abstract space, you want to map that space into a low-dimensional Euclidean space so you can look at the structure. Another optimization is to find web, which is done every time you do a search. You find the web pages that are nearest. Recommender systems we already discussed. Find the movies, books, what have you, near that you want. Actually, it's interesting, like the US Census Bureau uses recommender systems to fill in the blanks. You fill in a census form but leave out some fields. Well, it can see from your census form, you can characterize you, and then it can go and look at other census forms which have similar values for the things you entered, and then try to identify missing parameters. Face recognition is a good example. Image processing has lots of optimization problems, including recognizing faces and fingerprints and things like that. And as we'll see a little later on, distances are often very important here. Now, we have, when we look at loss functions, we have to do the continuous versus discrete. We mentioned that. Then loss functions have particular forms. The most famous for me is chi-squared, the sum of squares, observation minus model, all squared, summed over all observations. There is a hidden markup model, which you could view as an early version of a neural net, which just has a few hidden variables for corresponding to the observations, and and then you have a Markov random field, which generalizes that, but it's still not as general as a deep learning loss function, which has lots and lots of many layers of hidden layers and many and very complex connections. And in physics, we have free energies. That's the energy, including the entropy term, which is the kinetic term. And I pointed out how those get smoothed as you go up in temperature. I've already pointed out the greedy algorithms actually should not be dismissed. You should now realize they're greedy, and that has consequences. They're not exploring the space as fully as you might. You typically do greedy algorithms iterations, and each step you make the iteration that goes down as much as possible. If you think about a hill, you can move down the hill in many directions. but there's one direction that goes down the fastest. And in stochastic gradient descent, you have a set of small steps which go down the fastest. And if you go down your hill, you can choose how many steps you take. Now, if you're a person, you take a step, then another step, and then you see what happens. If you're a computer program, that takes too much time. You just take a step. Because you're taking lots of steps and lots of variables, there's not time to second guess them. With a single human going at a slightly slower speed, that's practical. Notice that Wall Street is full of local minima. Politics is certainly full of local minima. When somebody from a particular party gets in, they're often actually globally optimized, but in certain criteria, like a certain class of people or a certain set of criteria get used. You change the criteria, they're no longer obviously a minima. Or I should say optima. Well, recommender engines are a particularly good case of trying to discuss distances. If you do what's called collaborative filtering, which is the way the technique for deciding how to predict what people should look at, then one of the formulations, which is called user-based collaborative filtering, then you have a set of users and a set of items, and we're trying to match the users to the items. So you think of the users as a point in the space of items. So there's a space. If you have a billion items, there's a billion dimension space, and then the user rates items. So he has points in his vector, which are the weights, which means he has a lot of missing points in his vector. So this is not a traditional space. Traditional spaces do not have missing points, because remember, 0 does not mean missing. 0 means terrible. So when you rate, so these are interesting vectors which only have some of their components defined. And then there's something called the Pearson coefficient that takes these funny vectors and finds out effectively how near each other. And this type of idea is used continuously by, here it says last.fm, but Amazon and Netflix essentially use these ideas. Okay, so we can also do the opposite, which is item-based collaborative filtering. We can think of the items in a space of users. So a given item is, say, rated by 1,000 users. So its vector would have 1,000 entries, which are the ratings for those users. And so here we have a user space vector for each item. And again, we can find, here it's called the cosine measure for historical reasons, which is a traditional distance measure, effectively, which tells you how far these items are apart. Because again, you would expect if a user is looking at if a viewer watches a movie, and that movie has one of these vectors, then if you calculate the distance correctly, so only use the the points in common where they're both defined with common ratings, then points in the space which have similar ratings, which is what the cosine measure abstracts, are likely to be useful to view. All right. The last slide on distances in funny spaces does the other method for recommender systems, which are content-based recommender systems. Now we have a property space, which might be color, a size, age of interest, and things like that. Then you can represent each item in a space of properties, or which is a space of content, and then you're trying to find similar items, and so that's items that are near each other in this space. And that's again used by Amazon, Netflix, and Pandora invented this effect under the fancier name, the music genome. I think it was the foundation of their business. Well, do we need real spaces? Well, AI involves points. We have events when we're looking at physics and trying to find the Higgs. We have users or items when we're doing recommender engines. We have words and books and documents. And you can think of all these things we're looking at as points. They're in some space, which is sometimes called a bag. And then we want to look at, say, the set of all documents, which might be characterized by the occurrence of words. So they could be defined in the space of words. And we then need to see if they're similar, and we need to find a distance between them. And this distance, we'd certainly like it always to be positive. We'd like it to be symmetric. But there is this fancy Euclidean property of Euclidean spaces that DAB plus DBC is greater than DAC. That's the so-called triangular quantity is not true. So these fake spaces do not have the triangular inequality. And that is actually not a big deal as far as I know. It's just it's a property of Euclidean spaces, which probably leads to lots of useful features, but it is not essential. All right, most, for instance, deep learning is what I call here continuous optimization. Namely, it's you have a function. That function is a functional variable. It depends on variables. Those variables are continuous. And then we will next go on to discrete. But when you have continuous, then you get these plots like this. And here we actually somehow have sketched on here the path to the minima. So here is a path to the minima. And here is a rather clearer path to here. And you can see how it's done by a set of little steps which actually go in the local direction of steepest descent. So steepest descent, you can't do a steepest descent to the true minimum here from here, because the steepest descent direction's in this direction. So what you do is you just do an iteratively a set of steepest descents. Each time you go in the steepest descent direction, and say if you don't get trapped in the local minima, you will actually make it. And in the case of deep learning, we actually do lots and lots of these steps, huge numbers. And each time we do it sort of statistically in the right property, because we just use a sample of the data. And we do that partly to speed it up, but also this gives us lots of little steps. And by having lots of little steps, we have a much better chance of getting over these, getting through these fake minima and roaring off to the real minima. Notice actually in physics uses a different way of doing statistics. It uses the statistics of smoothing the function, which is the potential energy, with the thing you usually want to minimize is essentially the potential energy of the physics problem, with the kinetic energy terms, which have typical energy, as I mentioned, kT or kT over 2, and those are used to smooth out the problems. And so all of these methods actually use statistics in some sense to get the right answer. And we have algorithms, which are these ones here. These last three are the ones I used to use before I did deep learning. They're the classic ways of solving nonlinear optimization problems, and they're still probably valuable. I'm not quite certain when they work and deep learning doesn't work, but deep learning can do some of the cases I used to do here. And these tend to use they can use either first derivative, they can use function evaluation. Most of these use second order methods, Smakov explicitly. And Levenberg-Marquardt is also second order. And so these are basically second order methods. And for the problems we used to do in those days, they were not so big that you couldn't use second order methods and calculate a second order differential for the loss function. If we look at discrete optimization, then actually deep learning is good at discrete optimization. It learns, say for instance, whether a particular picture is a picture of the letter A, B, C, D, E through Z. So that's a discrete optimization, because we're just trying to find a discrete value, namely one of 26 possibilities for each of the pictures we have. Genetic algorithms are perhaps more important, although they're not as powerful and revolutionary as deep learning. And they sort of use the principle which is done by evolution. So convolutional neural nets actually use the method the brain does. So it's equivalent to a neural net in the brain. Genetic algorithms are basically evolution. So they have a set of, if you have a function you want to minimize by genetic algorithm, you form a bunch of function values, and that's your population. And then you're going to try to take that population and use the survival of the fittest method. And you often tend to use this for discrete problems, because it's much more natural with discrete problems, although it's not essential. So you have a set of points. They're the possible solutions. You have their fitness, which is the value of the objective function or loss function. And then you change the population. You delete things according to rules. You keep things according to rules, and then you mutate them, which you can do by, like in the way nature does, by cosmic rays wiping out a genome or something. I mean a DNA unit, or crossover, which is equivalent to marriage. Giving birth, where mating rather, where you take two vectors and then you merge them together and take, say, this part of one vector and this part of the other vector. And you take this, you take a large population and you iterate this population, and at the end you take the best value. And when you do deleting, you're not going to be deleting the ones that are doing well. This method only uses function evaluation. There's no derivatives being needed, and so it actually can run a lot faster than some of the other algorithms. Finally, we'll talk about heuristics. Here is Wikipedia's definition of heuristics, which are these ad hoc algorithms which you do, which are application dependent, and they are not exact, and they sacrifice something, and then usually the exactness, in order to get a method which can be run reasonably fast and gets reasonably good answers. Because actually, when you think about data is not precise, so you don't actually need the exact optimal for most sets of data. You just need a good optimal, and that's what heuristics are aimed at. They're aimed at good answers, not exact answers. And there's this concept in computer science called NP hardness, which essentially says it's an exponentially hard problem. But if you actually compare the property of NP hardness with how hard it is to solve, the many NP hard problems are actually pretty easy to have a good heuristic. And so heuristics are very, very important. And I would actually consider the constraints of being or not being NP hard are not as important as you might have thought. Thank you. So that's the end of this lesson, and let's get on with the next lesson.